Consider a language with a single object constant a and a single unary function constant s. There are infinitely many ground terms in this language, arranged in what resembles a straight line. Starting from the object constant, we move to a term in which we apply the function constant to that constant, then to a term in which we apply the function constant to that compound term, and so forth. In this section, we concentrate on languages that have linear structure of this sort. Hereafter, we call these linear languages. In all such languages, there's a single object constant and a single unary function constant. In talking about a linear language, we call the object constant the base element of the language, and we call the unary function constant the successor function. Although there are infinitely many ground terms in any linear language, we can still generate finite proofs that are guaranteed to be correct. The trick is to use the structure of the terms in language in expressing the premises of an inductive rule of inference known as linear induction. In general, if we know that a schema holds of our base element, and if we know that whenever the schema holds of an arbitrary element, it also holds of the successor of that element, then we can conclude that the schema holds of all elements. A bit of terminology here before we go on. The first premise in this rule is called the base case of the induction because it refers to the base element of the language. The second premise is called the inductive case. The antecedent of the inductive case is called the inductive hypothesis, and the consequent is called, not surprisingly, the inductive conclusion. And finally, the conclusion of the rule as a whole is sometimes called the overall conclusion to distinguish it from the inductive conclusion. In order to understand the intuition behind linear induction, imagine an infinite set of dominoes placed in a line so that when one falls, the next domino in the line also falls. If the first domino falls, then the second domino falls. If the second domino falls, then the third domino falls, and so forth. By continuing this chain of reasoning, it's easy for us to convince ourselves that every domino eventually falls. Now let's formalize this example and prove the result using induction. Let A represent the first domino, and let S represent the relationship between a domino and its successor in the line. Let's use the unary relation constant falls to express the fact that the domino given as argument eventually falls. Here are our axioms. We assume that the first domino falls, and we know that whenever any domino falls, its successor falls. Our goal is to prove that all of the dominoes fall. Here's a one-step proof of that conclusion. We start with the premise that the first domino in line falls. We also have the premise that the dominoes are so placed such that each domino knocks over the next domino. The nice thing is that these two sentences match the premises of the linear induction rule directly, and so we can derive the conclusion in just one step. Okay, here's a more interesting example. Recall the formalization of arithmetic introduced earlier in the course. Using the object constant 0 and the unary function constant s, we can represent each number n by applying the function constant to 0 exactly n times. Let's assume we also have a single ternary relation constant plus to represent the addition table. The axioms shown here describe plus in terms of 0 and s. The first sentence here says that adding 0 to any element produces that element. The second sentence says that adding the successor of a number to another number yields the successor of their sum. It's easy to see that any table that satisfies these axioms includes all of the usual addition facts. The first axiom ensures that all cases with 0 as first argument are included. From this fact and the second axiom, we can see that all cases with s of 0, or 1, are also included, and so forth. Now, in order for our definition to be a complete definition, we also need an axiom limiting the value of plus, the third argument that is, to a single value for each pair of inputs, which are its first two arguments. However, we do not need that axiom for the purposes of this example, and so for the sake of simplicity, we'll skip it. The first axiom here tells us that 0 is a left identity for addition. 0 added to any number produces the number of results. As it turns out, given these definitions, 0 must also be a right identity. That is, it must be the case that for all x plus x0 is x. Let's prove this. As usual, we'll start with our premises, the left identity rule, and the other rule defining plus. We use universal elimination in the first premise to derive the sentence on line 3. Plus of 0 and 0 is 0. All right. This takes care of the base case of our induction. We then start a subproof and assume the antecedent of the inductive case, plus of x0, x. We then use 3 applications of universal elimination on the second premise to get the sentence on line 5. We can then use implication elimination on this sentence and our assumption to derive the conclusion on line 6. We then discharge our assumption and our subproof and form the implication shown on line 7. X plus 0 equals x implies that s of x plus 0 equals s of x. We universalize this to get to the result on line 8. And finally, we can use linear induction to derive our overall conclusion, the sentence shown here on line 9. For all x, x plus 0 equals x.